Hello, this is Mr. Steenerson, and welcome to this mini lesson about the conservation of energy. I'm going to take you through a problem that involves a sled running down a hill, and we're going to analyze the energy at a couple different spots. Please have your notes ready and make sure you jot down any important details. Thanks. Okay, in this example, I'm going to talk about a child sliding down a hill and the energy that's involved at different spots along the way. We're going to look at two places. At the very bottom, which is place A, we'll analyze that first, and then partway up, which is part B. The energy relationship breaks down as the potential energy plus the kinetic at the top is equal to the potential plus the kinetic at the bottom. Substituting in the values for the equation, we can use mgh for the gravitational potential energy plus 1/2 mv squared for the kinetic. Notice I put 0 in at the potential energy at the bottom because we're using that as the 0 reference spot, so there is no height at the bottom of the hill. Looking at the initial potential energy, we'll use the height of the hill, 7.34 meters. And then we're going to, because mass shows up on both sides, we can just cancel the mass. So even though it gives us the mass is 50 kilograms, you can use it or not, you're going to end up with the same answer either way. Substituting in then the remaining values, then we can find the speed at the bottom of the hill, solving for the velocity at the bottom. And we end up with about 12.65 meters per second. So using the energy, we've just figured out how fast the sledder would go on a frictionless hill at the very bottom using our conservation of energy relationships. Now let's take a look at point B. And what point B gives us is a little bit more information about the height, and notice it's not at the very bottom of the hill. And so when we look at our energy relationship, we'll still talk about the kinetic energy and the potential energy at the top of the hill, in assuming that there's an initial speed. But we're also going to have to include some of the potential energy where we're analyzing it. I know it's not at the bottom of the hill, but if we're analyzing at point B, we'll have to talk about the potential energy at point B and the kinetic energy. So to solve for this, we'll set it up again with potential energy plus kinetic energy at the top, and the potential energy at point B plus the kinetic energy at point B. I'm just using bottom, whereas we're just going to assume that the point B is the bottom of the hill. Substituting in my equations again, we have mass times gravity times height for that initial potential energy. We can use the same height here because that's not changing any of the initial conditions. And then when we get to the mass times gravity at point B, then we're going to use the height at point B. So in this case, we'll have to substitute in the 2 meters. And then we'll, again, solve for velocity, so we're going to use the kinetic energy. Canceling out the masses, because they show up on both sides, we can then substitute in the remaining values. So the acceleration of gravity times my 7.34 meters. That's going to give me the first term there, plus 1/2 times the velocity at the top, still 4 meters per second. So we have a lot of the initial conditions are the same as before. And now we have this new potential energy, so we have some height based on the 2 meters, and then plus the 1/2 times the velocity at point B squared. Solving for that velocity will then be our answer, and I'm just rearranging the equation to solve for that v squared. And in this case, velocity at that point is 11 meters per second. Makes a lot of sense that we're not going quite as fast as we are at the very bottom, because not all of the energy has turned into kinetic energy at that point on the slide. Thank you, and have a great day.